All right, so we move on from our mediastinum here, and now we go to the pericardium itself. Now, the pericardium is going to be the technical name, the singular term to refer to the only sac-like structure around the heart. So it's the same thing, kind of like pericardial cavity, but what's the difference? Pericardium is all of the structures associated with that cavity. The cavity is just the space where the fluid is flowing. That fluid was called serous fluid, we've mentioned in earlier sections. This is that lubricant that's inside of that sac that helps with the cushioning of that heart while it's pumping. And we can actually nickname it now pericardial fluid. And so if we apply it to our images, if we look at the pericardial sac itself, you can see that the sac has two layers to it, an outer cover or an outer membrane, an outer wall, and an inner wall that's in contact with the organ. So one outer and then the other one's inner. And in that space in between, this is where the serous fluid flows. This is the pericardial cavity. It refers to this space. The fluid would be within that space, serous fluid. Now, the name of this layer versus this outer superficial layer, this is called the visceral pericardium, the layer that's in contact with the heart, visceral. Parietal, like the parietal lobe, the parietal skull bone, the parietal bone. Parietal in Latin means outer. So this is saying the most outer, or even superficial in this case, but the most outer wall. And so at the end of the day, these structures make up the pericardial cavity. The inner wall, the outer wall, visceral pericardium versus parietal pericardium. And they contain serous fluid. Now, something that's not drawn, and I kind of am re-emphasizing it here, is that there's going to be one more layer we're going to talk about, and it's not really related to this pericardial cavity, but it is a layer on the outside that contains connective tissue. They only show you a piece of it out here. This white texture on the outside that would be all around the heart is called your fibrous pericardium. And they illustrate it on this segment here as well. Fibrous pericardium here. And so fibrous pericardium is on the outside. Now, something to address now, that if we look at this fibrous pericardium, the outer fibrous tissue here, then we've made it to the outer wall, the parietal layer. This is the parietal layer, that is this wall here. And when you look at it, it should look pretty familiar what it is made out of. It's made out of areolar tissue. That's going to be right there at number 2. Let's put that number back in there, number 2. And number 1 is going to be mesothelia down there. And mesothelia was simple squamous. We've learned this term in tissues. This is simple squamous. You can even see one cell, another cell, another cell, lined up in a simple arrangement. They are flat cells, and so simple squamous. And that's what creates serous fluid or pericardial fluid. It's secreted by these mesothelia. And so that's what this wall looks like. That's what this wall looks like. They secrete pericardial fluid into that pericardial cavity. And so the pericardium is made of these layers. The most superficial will be the fibrous pericardium. The serous pericardium is made out of 2 layers, the parietal and visceral pericardium. Visceral and outer one, parietal. So that's here for you. Outer parietal, and the inner one is called visceral. They're going to be the 2 layers of the heart. They create that inner cavity that has serous pericardial fluid, and that's the pericardial cavity. We'll have one more annoying thing to add after this. It'll be confusing, but it'll involve these 3 structures. So take a moment. Cavity made by 2 layers. The 2 layers together are called serous pericardium because it contains serous fluid, which is pericardial fluid. And there's an outer layer called fibrous pericardium. These will come back in a second. We'll need them again. Now, we're going to quickly examine the blood vessels before we actually get into the nitty-gritty of the heart. We finished blood vessels today. And so we look at blood vessels, and now we're going to analyze what exactly they're made out of. And it turns out that there's only 3 layers you need to worry about in blood vessels. These 3 layers will have the same name, whether it's an artery on that side or a vein on this side. I know my screen blocks a lot of your view there. So this one up here is your vein. This one is your artery. If you look at it under a microscope, arteries always tend to be much more circular and have a deep middle layer made of a lot of smooth muscle. This is where you find smooth muscle. These muscles, they can either widen the artery or make it narrow. And so smooth muscle. The vein, not so much. They don't have much smooth muscle. And if you remember the jugular foramen of the skull versus the carotid canal, the carotid canal had a circular look to it, a canal. That's where the carotid artery goes through. The jugular foramen, do you remember it had this bean-like shape to it? And so that's because veins tend to be much more wider, droopier versus arteries. And so veins tend to have a larger diameter versus arteries. First notable difference. The second one is that the layer is thicker on the artery. And so these layers are named after their arrangement. You have tunica intima, like intimate means really, really personal, right? Really intimate, very close inside of you, innermost part of you, innermost layer. So it's the deepest layer. And as a rule of thumb, when you're looking at arteries and veins, arteries are always painted red on diagrams and models. Veins are always painted blue, except in the lungs. That's a big fact you need. Except in the lungs, the rule reverses. In the lungs, arteries are blue. In the lungs, veins are red. Okay, we'll be saying this point a few times in maybe more practical images, so don't worry, but this is a good introduction to it. Endothelial cells, if you look at this tunica intima of both layers, the most intimate, the most deepest layer is this one that's in contact with the lumen where the blood is flowing, where plasma and all those formed elements are flowing. Tunica intima is the first layer, and if you look closely, it's made out of simple squamous. And the simple squamous make the line. You can see a flat cell, flat cell, flat cell. This is another word for the simple squamous found in blood vessels. Mesothelia, the term we saw previously, was simple squamous found inside of the pericardial cavity. This is a blood vessel. So it's simple squamous, but it's found in blood vessels. And this tunica intima is going to have something called an internal elastic membrane, and this membrane helps with expansion. Remember I said that these arteries can expand or they can retract into a smaller size. They can stretch because they have elastic protein fibers, the same ones that make up the ear. These are made by elastic fibers, and so they allow for the expansion and recoil of arteries. Recoil means go back to their original shape. The tunica media is the layer that follows. And just quickly, before I move on, veins have the same build. Endothelium, simple squamous cells, and they might have some connective tissue, but they don't really care about having elastic membrane. So that's one big difference. The intimate layer, the intima, it does not have as many or at all elastic fibers like the arteries do, because there's not a lot of stretching going on in the veins. Tunica media is where there's the substantial differences. Because in that middle layer, you have smooth muscle in the arteries. You also have it in the veins. It just happens to be larger in the arteries. That's something you should notice from the photo. On top of that, that smooth muscle allows for two actions, vasoconstriction and vasodilation. Vasoconstriction means when the vessel is constricting, getting smaller. Think about a boa constrictor, a snake that wraps around its prey, and then it squeezes it until it dies. So constriction is squeezing together, making smaller. Dilation is like when your pupils are dilated, that means that they're large, so that means increasing the diameter. So when you're going from large to small, vasoconstriction. From small to large, vasodilation. And the arteries have an external elastic membrane. They need that extra elastic fibers to allow for some extra stretchiness. So you can see the external elastic membrane is going to be the boundary between the smooth muscle and the last layer called the tunica externa, which means the outer layer, tunica externa. And all I need you to know is that that layer, whether it's arteries or veins, it anchors vessels to the surrounding tissue, which makes sense. It keeps it anchored to wherever it's located. This is how it's glued to the surrounding structures. So tunica externa, tunica media. The tunica media has elastic membrane on the outside and an internal elastic membrane. It's sandwiched between elastic membranes. All right, remember that. Internal layer, external of elastic membranes. And this is what allows them to expand and recoil back to their original shape. You'll notice not really much is mentioned about elastic fibers in the veins. And they also don't have a thick, smooth muscle layer. But they have the same tunica externa doing the same thing, anchoring it to blood vessels. And so they also do not have that internal and external elastic membrane. Take a moment to write this down. Now, as we progress to the next slide, we are going to go in the numerical order. We might have to edit a little bit here, but this is a sort of a typo there, 1, 2, and 3. And so we are looking at the heart, and I want you to become acquainted with this photo before we get started. And you're learning vessels now, early, the gross anatomy. This blue one here is our PT up there that we sing in our key. That's your pulmonary trunk. And pulmonary, when you see that word pulmonary, will always be a reference to the lungs. Okay, the lungs. And so our rule flip-flops. Remember that we said that arteries are red, veins are blue, except if they're dealing with the lungs. And so that pulmonary trunk there is technically an artery. I wrote it there in parentheses. It's an artery, but it's painted blue. Next one. We have our aorta. This is a classic artery, so it's just an artery. It's painted in red. That aorta is the most elastic artery you have out of all of them because they have to be. It's receiving all the pressure of the heart, pumping blood into it so it can send blood to the rest of the body, and so it needs to be pretty elastic. The next two veins we have, you have superior vena cava. That's going to be SVC. And IVC for inferior vena cava. So superior vena cava, inferior vena cava for the vein. And those are classic veins. Now, if we start there, our elastic arteries are usually going to be, what we're talking about is the types of blood vessels that exist. So, if you find an artery directly attached to the heart, it is going to be an elastic artery. We just saw two. We have the pulmonary trunk, the PT. We have the aorta. These are two very elastic arteries because of how close they are to the heart. All that strength means that they have to expand, come back, expand, come back. And so elastic arteries, these are the largest ones that can stretch and recoil. The muscular arteries, these are the ones that go to the organs. Whenever you look at the models now and you see those arteries that are attached to the muscles that go through the muscles, those are muscular arteries because they distribute blood to the skeletal muscles. These typically tend to be medium-sized arteries. And if the arteries are going to the organs, then they're probably going to serve internal organs. We haven't learned this yet. We learn this next week. Okay, so for now, just skeletal muscles will be okay. And don't forget that at the end of the day, skeletal muscles are organs. And so these arteries deliver blood to all the organs of the body. That would have been a better term for these arteries. Organ arteries or something. But it's okay. Now, arterioles. We are ending our arteries. And arteries, at the end of the day, if we look at our illustration, no matter where they're serving the body, they go from being elastic arteries, and then as you go away from the body, they become muscular arteries. And then finally, arterioles is when they arrive to the organ. This represents, it could be a lung, it could be a liver, it could be the heart muscles, any of the skeletal muscles. They all need nutrients. Everything in your body is connected to your blood vessels by capillaries. And so as things are circulating, the smallest blood vessel is called arteriole, and this is now where it's going to drop off oxygen, and those blood cells make their way back to the heart. All right, so that is the difference there. So arteriole is going to be the small little blood vessel leading into the capillary, arteriole. And it's the beginning of the capillary. And so what makes them special is that arterioles means little arteries. They don't really have an outer layer, a tunica externa. And their tunica media is very, very thin. And they serve as the beginning of the capillary beds. Now, the cool thing is that at certain organs, this area of exchange, how we said that this is where things get dropped off, the nutrients, the gases, and even wastes come back in, and they get delivered to the kidneys to be removed. Again, everything in your body has this to deliver the nutrients. That's how oxygen gets delivered. But there are some organs that demand faster passage of materials. There are some that are just regular. So when you look at this purple region, depending on the organ you're looking at, you may have these type of capillaries, which are pretty consistent, or you may have capillaries with pores. That's what fenestrated capillaries mean. So for now, we write fenestrated means windowed or pores. And those allow for faster diffusion, faster movement across the capillary. You need these in your kidneys. More on these later. And so for now, this region, if you're building a capillary, depends on the organ you're at. You would put continuous for regular exchange. If you need fast exchange, you would replace it with fenestrated capillaries. And so the capillaries, their main objective, though, for now, your introductory material, is that they allow for the exchange between the blood inside of those capillaries versus everything outside, which is also called interstitial fluid, the shared tissue fluid. And because the walls are so thin, things can diffuse much more easier, and they're able to pass through the endothelial cells, the simple squamous of the blood vessels. If you look at capillaries, they are nothing but simple squamous cells completely making a tube up. Flat cells making a tube. These simple squamous are called endothelia. And so they're able to pass through capillaries easy. That's the goal of our capillaries. On the next page, you'll see that there are three types technically. We'll talk about them next. Now the veins are easy peasy. Venules are going to be the receiving side of when blood is flowing. These small veins are venules. So they kind of form the collection area for the capillaries. They collect blood from the capillaries. Then those little venules will then go on to become medium-sized vein. I really don't need you to, all I need you to know is the order of size here. Venules, then they lead to veins, medium-sized. And then finally, all blood returns to the heart by the large veins, which you know as superior and inferior vena cava so far. And so blood circulates through your entire body through these types of blood vessels. First, the large elastic artery, the aorta, travels to the organs, the muscles with muscular arteries. When it arrives to the organ or the muscles, it then creates capillaries, and then the beginning of the capillaries, arterioles, it drops off oxygen, nutrients, gases, I guess I already said it, gases, nutrients. It picks up waste at the organ, the muscles, and then the blood cells, once they drop off their oxygen, they flow back, flow back, flow back to the heart, and then the heart will send it to the lungs. Those red blood cells will get reloaded with oxygen, and the process repeats itself all over again. And that's how blood circulates through these blood vessels. And we end today just on examining the big picture, really tying it all together. We zoom in on a capillary. And you can see the red is our little arterioles, this one. Our venule is this one. And so blood flows through this arteriole, and while it's flowing, it lets blood cells go through the capillary bed. And here I drew my own thing. You might have to draw it on the side. But if you look at it, what would occur? Remember that red blood cells can organize themselves into rolu. Do you remember what that means? It means that they can stack themselves like chips when you go gamble and there's chips. And so they can stack themselves in order like this. And as they travel through the capillaries, those same red blood cells with their hemoglobin inside drop off oxygen outside of the capillaries. They pick up CO2, and now CO2, these red blood cells will carry CO2 and deliver it to the lungs to be removed. But at the same time, they dropped off their oxygen. Now, this picture, I love it because these cells can be anything. These cells can be any organ in your body. They're waiting for oxygen because their mitochondria need oxygen. Your mitochondria needs glucose. Glucose, a carb, is coming through here. Glucose leaves. Now these cells use glucose. They use oxygen. They drop off their CO2 onto those red blood cells. And don't forget, these cells, in using all of the nutrients, carbs, protein, lipids, and in using oxygen, they produce waste. Urea, ammonia, bilirubin, other examples. I only gave you urea and ammonia. And so these wastes go into the plasma and they get removed by the kidneys. Eventually, they get delivered to the kidneys to be removed. And so every organ in your body is built this way. Your skin, the capillaries underneath your skin, capillaries are your organs, the capillaries are your muscles. The capillaries are a drop-off site for what's needed, a pickup site for what is no longer needed, like waste and CO2. And then it just continues that at some point, these same red blood cells, they pick up CO2, they go to the lungs, come back eventually, and do this all over again. For up to, how long do red blood cells stay alive for? 120 days, 4 months. What organ do they go to be recycled? Anybody remember? The spleen. And so this happens over and over and over. Waste is removed by the kidneys. Oxygen is put in the blood vessels by the lungs. We'll get there tomorrow. CO2 removed eventually. And so I'll start here again as a little recap. I just want to finish up this last little capillaries, and we're done with blood vessels, and we go back to heart tomorrow. And so capillaries can be continuous. They permit just regular diffusion as far as you're concerned. They're continuous, meaning they don't have pores. They just look like fully built cells. So the endothelium is complete. The lining is complete, meaning that they don't have pores. This permits just regular diffusion of water and small solutes. That's their job, to permit things that you need to go into the tissues. Water, as an example, or small solutes like ions. The fenestrated ones are the ones that are found in the kidneys, and also found in areas where you need good absorption, like your intestines, to absorb the nutrients that you need in your plasma. So capillaries in your intestines, they are built for good absorption. So all those useful nutrients are going into your bloodstream. In the kidneys, it's so that all the waste can exit the bloodstream. We'll get into details when we get there. But these locations I need you to know as the example where you find pored or windowed capillaries. We call them fenestrated. And the goal is rapid exchange. The last form of capillaries not mentioned before, these are found in the liver. These are huge. They just have huge pores. And so sinusoids, from the word sinus, you learned sinus means like huge pocket, huge opening, huge space. From where you're learning the skeleton, it's named after that. Sinusoids is going to be a vessel that has huge openings that essentially are like cavities. And so these are found in the liver, and they are there for, I want you to really learn it easily, for extra large molecules. And in your liver, don't forget, your liver is where you make plasma proteins, albumins, globulins, fibrinogen. These can be pretty large. And so the sinusoid capillaries are perfect for letting them out when they're built or receiving them to recycle them. You never really know at this level. We're really kind of just keeping things general and simple right now. And so with that, this concludes this first part of the video. Tomorrow we record the next part.